Here is an arrangement for comparing several HF receivers. There is a strong signal coming in to this attenuator. Those signals go through this notch filter, which has a very deep notch about 3 kHz wide at near 14 MHz. The output goes through a 6 dB attenuator and then into a hybrid. This hybrid splits the signal, the strong signals, into two parts with the same amplitude. And into the hybrid there is also another signal from a signal generator, which is split also equally between these two output ports. Then the output goes to a hybrid that splits into three outputs. One is the Airspy+Spyverter combination. The next one here is an HamItUp converter that converts from HF to 125 MHz plus the HF frequency, and that is received by an rtlsdr dongle, this one. And the third output goes through an attenuator of 4 dB and into a Perseus. On the other side there is also a 3-port hybrid. One goes through a 10 dB attenuator and into a BladeRF with the B200 converter. This has a very low noise figure, and it wouldn't be unfair to test it without this 10 dB attenuator. And this port goes to a little radio here, Soft66rtl. That's equivalent to the HamItUp and the rtlsdr, but it's in a box. Then the last port goes into, where is it? This cable comes in here, attenuator, amplifier, one more attenuator and one more amplifier, and then this box. This contains another BladeRF, but the input is directly to the A to D converter. So there are two inputs, one has a dummy load and the other has the signal. And since the input is directly to the AD converter, it's necessary to have some gain. And this combination of attenuators and amplifiers gives the desired gain without adding any noise. The 6 dB attenuator on the output of the notch filter is there in order to present approximately 50 ohms also on the notch frequency to the hybrid, to get isolation between the two sides of the output, also on the frequency of the notch. I don't think it matters, but it could happen that the units send something out when they saturate, and that could cause interference in other radios. The loudspeaker output from all the receivers is routed into this instance of Linrod. They are all set for the same bandwidth, about 2.3 kHz, and the signal is here. That's the signal from this generator that goes directly into the hybrid. The hybrid is 3 dB, the 3-port splitters are 5 dB, and then there is additional 4 dB attenuation for the Perseus. So that sums up to 12 dB. We would expect 91 plus 12, that is 103. That's what we should expect to read on the Perseus here. And it's within a dB, so all looks good. Linrod is set to measure the power of the entire baseband here, except for those points which are red here at the center. Those points are this passband and a little bit outside, and there the signal is. So the ratio of what comes through this narrow filter and what comes through this wide filter is the yellow curve that you can see at 0 on this graph. So that is the noise figure for this radio with an offset and reversed sign. It means that if I, let's say, change the amplitude of the generator by 5 dB, like that, plus 5 dB, you can see that the yellow track goes up by 5 dB. But the white does not, because there is an AGC. 5 more dB, and signal to noise ratio goes up another 5 dB. I have set all the radios to show 0 when measured on the audio like this, and to have the same bandwidth here. When I switch off this signal, like that, we can read the noise floor of the Perseus as minus 118.6. The bandwidth is 2.27 kilohertz. The logarithm of 2270 hertz is something like 33.5. So adding that to 118 gives us 152.1. That differs by 22 dB from 174, which is room temperature, Boltzmann's constant and 1 Hz bandwidth. So the noise figure is 22 dB on the input of the Perseus. Now there is a 4 dB attenuator. It means that the noise figure at the output of the 3-put hybrids, all the 6 outputs, is 26 dB. So this means that this study of dynamic range is measured at a noise figure of 26 dB, which I think is a reasonable point to do measurements for noise figure on HF bands. Different radios may require an external attenuator. Others have internal level settings that don't destroy dynamic range. But comparison is made on an equal noise figure, and that's the fundamental thing to worry about. I have calibrated the S-meter graph on all the different radios to 0 for those that use Linrod. Here, that's the HamItUp converter. I don't know if the camera can catch this. And here is 0. And here is the BladeRF using the converter and the tuner in the box. And it shows 0. And the one that goes directly into the what? Oh, it crashed. So here is the direct AD. I have restarted it, and now it shows 0. This is Windows 10. It was quite stable before, but I did an upgrade and it's not so stable anymore. That's the big problem with Windows 10 that I see. One has to do a lot of work to install proper drivers to replace those that Microsoft insists to install. The SDR Sharp, the Airspy, is routed to the loudspeaker. All the others are silenced. And here is what I see on the loudspeaker output. And I start the signal generator. And you can see the yellow track shows 0 because it's calibrated just like all the other ones. I mean, the gain is set to provide a 26 dB noise figure at the point of the hybrid output. The lean rods show 15 dB signal to noise ratio. 15 dB. 15 dB here. It's the this is the BladeRF with the tuner, and this is the BladeRF direct AD. And of course, the red track is the signal, the input where there is a dummy low that shows nothing. And here we have about 16 dB. There is an inaccuracy of about 1 dB in these measurements. And here we see 103.7, it was 118.7 before, so it's a 15 dB signal to noise ratio in the 2.31 kilohertz bandwidth. So this is the basis of continuing measurements. In a two-tone dynamic range test, the first to fail is the BladeRF with the tuner on it. I switch on the strong signal, and you can hear the noise goes up, and I have set the level for a 3 dB loss of signal to noise ratio. And you can see the intermodulation is not very strong, so the problem here is reciprocal mixing. The reciprocal mixing occurs for an input signal level of minus 65 dBm, and that's it at the noise figure of the noise figure of 26 dB. The two signals, about 20 kilohertz, this is the frequency where I'm listening. This is one of the strong signals. This is the other one. They are about 20 kilohertz and 40 kilohertz below the signal frequency. They are amplified, 6 dB amplifiers, combined in this combiner and then run through the notch filter. And you could see the signal level just recently. The attenuation I had to set to get the minus 65 dBm level happens to be 65 dB. Increase the strong signals by 10 dB. and you can hear the noise goes up, and we have now a 10 dB degradation, but the third order did not change much. Another 10 dB, and now the third order is a little bit stronger than the signal, but the noise is very much stronger. We have a 23 dB signal to noise dB loss here. So the problem with the BladeRF and the B200 at close range, that means 20 kilohertz, is reciprocal mixing. So I go back to the level where we had the 3 dB degradation here, and now I switch from the tuner, set the gain here to 0, and then I go to this one, the direct AD, and turn up the audio. And you can see here, it shows 0. So I turn up the level of the strong signals. That's 10 dB, it's too much. Something like this, and you can see it varies by time. It's because it is the digital feedback, and which behaves in a little bit odd fashion. The digital feedback, it comes in both the green and the red channel here. I don't know why it varies by time, but it's something about the phase relation of the digital output and the input. Anyway, at this point, the third order product here gives equal amount of power as the entire noise from here to here, excluding a little bit at the center. So this is what I see on the yellow track. It goes up and down like that. The level where the direct input starts to lose 3 dB is minus 60 dB on this. So it is 5 dB better than the BladeRF with the up converter. Now I have switched to the Soft66rtl. It looks like this, and here is the signal to noise ratio, and I need a little bit more of the strong signal. 10 dB would be too much. It's like that. But here is what it can tolerate. That is 55 dB on this attenuator. The HamItUp with the RTL-SDR is here. It has a different setting, but the result is very much the same. I increased by 1 dB. And the level is the same as for the Soft66rtl. I have now enabled the Airspy, and I can turn the level up a little bit more, not so much, but 1 dB, 2 dB, 3, 4, 5, 4, 5, maybe. So that is 50 decibels. Now, what we see here is probably digital feedback, so I increase the level a little bit more. That was just to verify that the signal level didn't go down again, I mean the interference level, and it didn't. And finally I look at the Perseus. We can see the third order here, but it is the digital feedback and it doesn't grow much with signal level. It degrades signal to noise ratio by maybe 2 dB. Then I go up 10 dB. Now 20 dB. Now it's strong. So I go back 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So this seems to be the onset of real non-linearity in the input stages. So the 3 dB loss is maybe something like this. And I don't see the intermodulation tone at this point. I have to verify that intermodulation sent from the other radios don't enter the Perseus. Now I have replaced the other radios with dummy loads, and you can see the Perseus now is not disturbed at all, so I have to put on more signal level into it. 10 dB more. Another 10 dB. Now it is rather much disturbed. So here we have the point of 3 dB loss in the Perseus. And that is 18 dB on the attenuator. I have now reconnected the Airspy. Having the Airspy, the Perseus connected, but all the other ones disconnected. And then I look at the audio from the Airspy, and I find that I have a 4 dB degradation. That is at 50 on the attenuator. 51 gives 2 dB SN loss. So the measurement on the Airspy was okay. It's only the Perseus with its much higher dynamic range that gets interference from the other radios when their inputs are heavily saturated. And the leakage goes into the Perseus despite the isolation of the hybrids. And here are the results so far. That is the close range performance in a two-tone test. And it also gives reciprocal mixing when doing the measurement this way. And it's an obvious, very big difference between a real radio like the Perseus and all the low-cost alternatives. They are interesting because of the wide coverage and because dynamic range is no longer as important as it has been on the HF bands for two reasons. One is that the noise floor has been higher now because of all the things, modern low energy lamps, computers, and internet over mains power or whatever. So the average noise floor is maybe 10 dB higher. And also the usage of HF is much lower now than it used to be 25 years ago. A lot of very powerful transmitters have shut down. Energy is expensive, and listeners to HF is not so. They are not so many anymore. So broadcasting for foreign countries with very high powers is less frequent now, and that has eased the requirements on receivers by maybe something like 20 decibels. I mean 10 dB on the power lower, fewer stations and lower peak powers, and they sum up to a lower peak total, and then the noise floor is about 10 dB higher. So it means that even though the difference is very large from the Perseus to the other ones are not useless. They can be perfectly adequate in many situations. As it happens, I forgot one thing. This filter, it attenuates the overtones that may be generated in the amplifiers or in the signal generators. Overtones would mix with the signal and create something by second order at the same frequency as where we have the third order intermodulation. I have disconnected all the radios except the Perseus and connected one of those 3 ports to the spectrum analyzer, and you can see we have minus 18 dBm. And here the attenuator is at 18. That's where the 3 dB point of degraded performance was on the Perseus. And I can see here it's still exactly the same. So second harmonics from the test system did not affect the measurements at all, not for the Perseus. I have verified that this low-pass filter, well, it has a notch, but it doesn't come into play in these measurements. This low-pass filter did not change the results I have shown at all. I now set the generators 400 kHz and 200 kHz below the signal frequency, the signal that is in the middle of the notch. And now I'm listening to the BladeRF with a direct AD converter input. And it looks exactly as before. There is this signal on the IM3 frequency, and it comes in both the channel where the signal is connected, all the signals, and the other channel on which there is a dummy load, because the digital feedback feeds back into both ADs. The level I have to set is 60 dB, and that is to get exactly the same as I had before, and BladeRF with the AD converter 60. This unit has no selectivity. It doesn't matter what the frequency separation is. This is the HamItUp with the RTLSDR, and this is what the screen looks like, and the signal to noise performance. It needs more signal. And that is too much. So this is what it can tolerate. Probably AD saturation. The level now is 55. And here is the Soft66rtl. And the level is still minus 55 dBm. And here is the signal to noise ratio. This one needs a little bit more signal to get the 3 dB degradation. And there it goes into saturation, so 1 dB back. And the level here is 51. So at larger separation, this one is a little bit better. I'm still at minus 51 dBm, and here is the BladeRF with the B200 up converter and the tuner chip. And you can see the IM3 is pretty strong. And indeed, I need to reduce the signal level a little. And here we have a 3 dB loss of performance. And that is at minus 54 dBm. So here is the Airspy. I have connected dummy loads instead of those ones who are already saturated. And look at the signal to noise curve here and turn up the level. So here is the point of a 3 dB performance loss, and it is minus 49 dBm. And finally, here is the Perseus at 200 kHz separation between two strong tones. You start to be able to see the notch filter here around the pilot tone. And we have the third order intermodulation here, or maybe digital feedback. Anyway, performance loss is now 3 dB. And I increase 1 dB, 2 dB, so this is the level. And on the attenuator, I can read 14 dB. Here is a table with the results I found on the two-tone test. Performance is significantly better on those units that have tuners. Also, the Perseus is a little bit better. I'm not quite sure what the reason is. Maybe reciprocal mixing, maybe something in software. It is just 4 dB, so I don't take the trouble to look into what is the explanation for this. The generators are now separated by 1 megahertz, 14, 13 and 12. Approximately. I'm still listening to the Perseus with all the other replaced by dummy loads. The degradation I see is 3 dB, just as before, and the attenuator is at 14 dB. 200 kilohertz or 1 megahertz doesn't matter for the Perseus. And here is the, and I need a little bit more than what I have now. 1, 2, that's too much. This is the appropriate level, 1 dB above what I had before, and it is minus 34 dBm. Here is the HamItUp+rtlsdr combination. It looks nice here. And here is the noise evaluation. And I increase the signal level 1 dB. 1 more dB. And now this is clearly more than 3 dB loss. So here is the level. And that is 40, minus 40 dBm. Here is the Soft66rtl at the same level, minus 40 dBm. And you can see intermodulation is stronger. The reason is that this unit intermodulates in the up converter. It is more favorable at 200 kHz because it has a better gain distribution. I have to set only 39 dB gain here, as compared to 49 for the HamItUp converter. But the HamItUp converter is not producing intermodulation as easily. So I have to turn down the level until I see a 3 dB loss here. And I'm going upwards in 1 dB steps, and here is the point of, well, maybe here. No, let's say here, for 3 dB degradation, and that is minus 42 dBm. The BladeRF with the B200 up converter, it looks like this, and here is the noise evaluation. And I turn up the level 1 dB at a time. 1, 2. Well, that's too much. So here we are. It looks like this. And this level is minus 38 dBm. And the direct input to the AD converter in the BladeRF looks exactly the same as on the other two separations. Since there isn't any selectivity, there isn't any difference at different frequency separations. And here is what we have here. Here is a table of the 1 MHz two-tone results that you have just seen. Dynamic range is pretty good for the low-cost units. The number of bits is not so important because the signals are outside the IF filter of the tuner chip. I have now connected a wire antenna, about 8 meters of wire, 25 meters away from the house, through a 30 MHz low-pass filter, and then a low-noise wideband amplifier. It's a modified AD6IW with much bigger coupling capacitors, 0.1 microfarad. This gives maybe 22 decibels flat gain from 100 kilohertz to a couple of hundred megahertz, and then it falls off very slowly. That's why I need this filter to get rid of the FM stations and the mobile phones and stuff. The amplified signal then goes into this class a wideband amplifier, and after that into these attenuators as before, but I had to remove this attenuator to get enough signal, which means isolation in this hybrid is no longer good at the center of the notch. I have now the Perseus connected while the other ports have dummy loads, except one which goes into the spectrum analyzer, which could be considered a good dummy load. In this situation, you can see the Perseus is almost okay, but occasionally there are problems, like here. If I increase the level by 2 dB, like that, you can see that we have problems more or less all the time. And you can see here there is ADC clip fairly frequently, and you can see the associated increase in the noise floor here. I have backed off to the situation where interference is not severe. You can see most of the time it is less than 2 dB or close to 0, but there are occasional occurrences of ADC clipping that create problems now and then. Anyway, the time domain signal at this level is, as you can see, about 7 volts peak to peak. It's a lot of signal. And I can see this because there is no other radio inserted in the system. It's just the Perseus and this oscilloscope at the moment. I can look at the time. If I set it to trigger better. Well, it seems like something strong has switched off. It's almost 1 o'clock in the night. If I look at the frequency information, you can see that something strong is about 1.3 megahertz. Something other is about 6 megahertz. Not quite as strong, but strong. With all the radios connected, the situation is completely different. The interference produced in the other radios couple better at the notch frequency where the hybrid doesn't isolate well anymore because the missing attenuator. And all the radios show complete total saturation. So the idea to use hybrids to isolate isn't good enough in this situation. What I will do is to step up the signal gradually from a low level and look into which receiver is first having a problem and then replacing that one with a dummy load. And the one that has a problem first is the direct AD input on the BladeRF. It looks like this at the current signal level, and I step up. And we can hear in the loudspeaker, and you can see here about 5 dB loss. Well, 1 dB less of signal. And it's 3 dB loss up to 5 dB. Fairly stable. And this is what it looks like in the BladeRF. And the BladeRF is wideband. You can see all the strong signals here. those that we could see also on the spectrum analyzer. I can change here a little bit. So we can see the medium waves and the lower HF frequencies. And this is the level that this unit can take. And I qualify that as 51 dB on the attenuator. So I disconnected this one, replaced with the dummy load. The next unit to have a problem is the Soft66rtl. And I look at it's the one to the loudspeaker now, and I look at the signal to noise ratio evaluation here. I increase the level by 1 dB. Well, 1 more dB. That is clearly too much. So 1 dB less. I think this is fair to say. Now we have a similar degradation as we had in the BladeRF Direct AD just recently. And the attenuator setting now is 42 dB. The next one to have a problem is the BladeRF with the B200 converter. It looks like this, and the S-meter evaluation like that. But the HamItUp with the RTLSDR is very similar. So I switch off the sound here and then enable the sound here. And you can see it looks more or less identical. And you can see also on the spectrum, and like here. So both the BladeRF with the tuner and up converter and the HamItUp and the RTLSDR, they get the problem at the level of 28 dB. And here is the Airspy. And the signal to noise ratio looks like this. It is certainly degraded. I give it 1 dB more. And now it is clearly losing. Well, not all the time. So I would say like this, 27 dB, 1 dB better than the previous two ones. And finally, here is the Perseus again, with all the others disconnected and replaced by dummy loads. Signal to noise evaluation looks like this. 1 more dB. Well, 1 more. And you see where 0 is. This is clearly too much. This is approximately the limit for what Perseus can take. And the attenuator shows 6 dB. And you can listen to the interference level, the characteristics of it, from the loudspeaker here. I remove the strong signal. And you hear some impulse noise disappears. That comes from overload somewhere. Might be possible to fix that by use of the noise blanket. And I look at the oscilloscope again. Fairly strong signals, a little bit different than half an hour ago, or was it maybe 1 hour? And this is what I see in the spectrum analyzer at the level where Perseus gets a problem on 14 megahertz at night. And you can see the level is well, towards 3 or 4 or 5 dBm here on the medium waves. And here it's approximately 0, but there are peaks up to 5 dBm or so. Here is the ranking list of these receivers at night on a wire antenna of a length of maybe 8 meters. So if Perseus is the reference, the good tuner and up converter units, Airspy+Spyverter, HamItUp+rtlsdr, or the BladeRF, they are at about 21, 22 dB with respect to the Perseus. This is pretty good. The Soft66rtl seems to have a problem with nonlinearities in the up converter, so it's not so good. And then the BladeRF direct input to the ADC. Well, the ADC doesn't have many enough bits for being used under these circumstances. It needs a filter to limit the bandwidth in front of such a unit. It's 2 o'clock in the afternoon. This is the wire antenna, and you can see now what is on the medium waves is very weak. There are signals all the way up to 19 megahertz. That's where the marker is. Maximum is around 10 megahertz. I have switched to a dipole antenna for 14 megahertz, and that gives a little bit more signals in this region. The cutoff at 19 megahertz is because of the notch filter. It has a upper frequency there. Now only the Perseus is connected, the others are replaced by dummy loads. I have switched off the AGC to see better here on the noise, signal to noise ratio evaluation. I can increase the signal level by 2 dB. And these clickings happen more frequently. And 2 more dB. And this is complete disaster, but not all the time. So I back off 2 dB again. And you can see there is AGC clipping now and then. They don't correlate to this clicking sound. Well, now there was a more intense interference. Of course, the situation is not constant. So I sit for a while and find a position where interference happens infrequently. And it is about this point. And I can read 16 dB on this attenuator. I have connected the Airspy now, and it does not affect the Perseus. But the Airspy is heavily saturated. So I have to reduce the signal. 10, 20, 1, 2, 3, 4, 5, something like this. And now it looks like this. occasional interference. Things are different on different receivers, of course, because they are sensitive to stations at different frequency separations. But this is somewhere around what the Airspy can take. Maybe I have to reduce my 2 dB too, like that. Well, one more. So there is interference now and then. This is what the screen looks like. And the attenuator is at 48 decibel. And you can hear now and then there is an interference. Now I've connected all the other radios and I'm still listening to the Airspy. And you can see at this time the interference is a little bit lower, but the other radios are fairly saturated. Well, I don't know. We will see. This one at least. But I think this level, occasional bursts of interference, that's where I rank the Airspy. And it was so listening to something else. Remove that and add this with the B200 up converter, and you can see there is a continuous interference that is at about 5 dB, and now it's stronger. So I reduced to something maybe here. Well, it's often above 3 dB. So about here is the BladeRF plus the B200, and that's 53 dB. This is the BladeRF still. Switch that off and go for the Soft66rtl. And this is clearly a little bit better. You can see no interference. The HamItUp converter, it has interference, you can see here clearly, and also the BladeRF. But the Soft66 is a little bit better. I'll go up, let's say 2 dB, and that seems to be too much. Now we have interference more or less all the time. So back off 2 dB and it's okay. So, well, not quite. It's very similar in performance. So I switch that off and go for the HamItUp. And it seems to be a little bit more interference, but not very much. And you can hear other kinds. Now it's really offended. And you can see here also, look at the waterfall. And also here. I don't have a waterfall for the Airspy, but I listen to the Airspy instead now. Sorry. So there is the Airspy, and I have to get rid of the BladeRF that I happen to switch on. So the Airspy, it's not disturbed, while the other ones, well, just at this moment, not so much. I have been listening at 52 on the attenuator, and now you can see the interference clearly in the BladeRF, as well as in the HamItUp. And not so much in the Soft66rtl. But I'm listening now to the Airspy, and you see there is nothing there. So I increase by, let's say, 6 dB. That's 10 and 9, 8, 7, 6. Five, 6. So this is a little bit hard to judge because the signal levels vary all the time, but this is something that the Airspy is reasonably happy with. Look at the waterfall here and the waterfall here. I mean baseband waterfalls. Or here, the spectrum. So I would say this is what is okay for the Airspy at this moment, and the other ones are about 6 dB worse, all of them. That is except for the direct input BladeRF, where I have to turn down the level to something like here. And that is 53 dB. And not too far from where the other ones actually were. So now listening to the BladeRF direct input, you can see here there is strong interference on the HamItUp and on the Soft66. And we can see, of course, on the Perseus the reason there is something close-spaced. It looks like this in the Airspy. And listen to the Airspy. And that signal is gone. I'm staying at 53 on the attenuator, and look at the waterfalls. The direct input has occasional fairly strong interference. The BladeRF with the B200 converter, it has also fairly strong interference. And here is the HamItUp also. But the Soft66rtl is better. It survives this signal level. And of course the Airspy, although I don't show the waterfall for it, it is what is in the loudspeaker, and it doesn't have any problems, as you can see here. not over the entire time period. It's now 4 o'clock in the afternoon and I have this set to 44 dB. Listening to the Airspy, you see the spectrum here and you see the notch here. And here is a waterfall of the output. Here we have some interference. And here you have the signal to noise evaluation. So the Airspy is more or less okay. You can see the waterfalls from the other radios. The Soft66rtl severely disturbed. Look at the S-meter graph here. The signal level goes up quite a lot. 10 dB of extra stuff. The HamItUp+rtlsdr, it's about the same, 20 dB, a lot of interference. The BladeRF with the B200 converter, it is a little bit better, as we can judge from the S-meter here, and also from the waterfall. While the direct input to the BladeRF is completely saturated. You can see the wide spectrum and you can see the, look here. The signal level is far above the 15 where it should be, and digital feedback gives a lot of signal. And I go back here as time has passed a little bit. HamItUp, Soft66, B200 with the BladeRF. So I switch off the Airspy and enable the BladeRF. And look here, and reduce by 6 dB. 1, 2, 3, 4, 5, 6. And I have to make sure that the carrier here has to be within the filter, of course. And you can see that the BladeRF with 6 dB, we have about 6 dB loss of signal to noise ratio, but now it's better. It varies from time to time, so about 6 dB is a good thing to say. And if you look at the Soft66, you see the S-meter here. I change and move the Soft66 to the S-meter, the signal to noise evaluation. Like that, and on with this, and you can see it's not very different from what we had here. Well, now it's not so good. It's the whatever this is, strong thing. I want to listen on the Airspy. While that is going on, and I add the 6 dB, and I wasn't fast enough. But it seems it doesn't affect the Airspy. That's probably digital stuff. Now there is probably a similar thing, but yes, here we are. So the relation between the Perseus and the Airspy, as you can see from the previous evaluations, is is not consistent. The difference between them is a little bit uncertain. So I have inserted a 25 dB attenuator in front of the Airspy, and I have increased the signal generator by 20 dB. That means that I see a 5 dB degradation in signal to noise from the Airspy. And of course, when I switch for the Perseus, I see a 20 dB improvement, almost, because the signal level is 20 dB stronger here. I have a problem with the linearity of the, well, I can go a little bit higher. So here you can see it indicates 20 dB more signal to noise ratio. And I turn up the strong signal until I have a problem. Oops. It's here. Well, maybe here. That's in the Perseus. And I can look at the Airspy. I look at the noise floor. You can see it makes excursions. If I listen to the Airspy instead of the Perseus, we see that now and then there is interference that is fairly strong. But at this time we have ADC clipping and also problems in the Perseus. So at 25 dB they are fairly similar. I do it like this. You can compare now on the baseband. Here the Perseus has problems, here the Airspy has problems. And they don't come at the same time, but they are of a similar magnitude. And you see here we have constant clipping, I have to reduce. So I think 25 dB is a good number to put as the relation between the Airspy and the Perseus at this time of the day. Here is the final ranking list from this study. The relation between the Perseus and the Airspy+Spyverter in daytime is a little bit larger than the 25 dB that I had on the attenuator. If you look carefully at the video, you can see that. 26 happens to be the average also between the two previous measurements that deviate significantly from each other. In daytime, all the others are fairly similar. It's because the bandwidth is a little bit limited. The strong medium wave signals are not present, and therefore the BladeRF doesn't get saturated as easily. At night, the medium wave kills the direct input to the ADC because the strong signals at low frequencies saturated. The Soft66rtl has a problem with its up converter. It saturates for the low band signals. The other three, they are fairly similar at night, but at day the Airspy is 6 dB better than the other three. So differences between the Perseus and the low cost are big, but there are significant difference between the different low cost systems. And of course, the direct input, it needs a filter. If you put the filter in front of the Soft66rtl to remove the low frequencies, it is probably a little bit better than those other two because it has a better gain distribution. AGC off in the Perseus because otherwise the gain through this radio goes down and stays down for a while after each interference pulse, and that disturbs the S/N evaluation. And these are the settings that affect performance. The Airspy decimation is set to maximum because that enables the narrowest IF filter in the tuner chip, the R820T. Sample rate 10 MHz. Use the highest sample rate because that reduces the noise floor. So away with that. Radio USB bandwidth 2.4 kHz. It should be 2.3 kHz, but it didn't make a big difference. Audio. AGC off. And the other things don't matter, I think. So the parameters for the BladeRF with the B200 converters, you can see here, bandwidth 1 kHz, window that is 9, that gives the best dynamic range, I mean best filter properties, the fastest transform, and 3 threads in parallel. That doesn't affect performance, it just reduces the CPU load a bit, and that could be important on a system like this where I ran several things at the same time. And first mixer bandwidth reduction, I set that to 8, not critical, and the number 8 window that gives a nice IF filter. And then, more important, the parameters for the BladeRF, the maximum sampling rate, that is to get the lowest possible noise floor, and then connection is through the SMA connector and the tuner. And I have set the narrowest low-pass filter that is available, and it is 1.5 MHz. The direct input has these parameters, very similar as you can see. And the same here, and the setup, it's also the maximum sampling rate, and it doesn't say so, but it is the input through J61. If you do the setup, it is A and then J for the BladeRF, and it was device number 0, I think. and input via J61. I say yes here, and then give the speed, and I don't resample because I want the full bandwidth, and I don't know anything about the crystal frequency. So that was the setup for the BladeRF ADC input. The Soft66rtl X and P, you can see it's very similar to what I had on the BladeRF, but since the sampling frequency is 2.4 MHz, the bandwidth reduction is a little bit smaller. The HamItUp has very similar or identical parameters, X and P, as you can see here. And X and U, and you see sampling rate 2.4 MHz, gain mode 2, that's the linearity mode, and the IF bandwidth is 300 kHz, the narrowest possible. And for the Soft66rtl X and U, it's the same parameters as for the HamItUp+rtlsdr. I mean, the electrically, a converter plus an RTL-SDR. I have set the same parameters in both cases. The only difference is the gain that I have set on the processing screen. I talked about that earlier. Here is the frequency response from the antenna input on this low-pass filter and to the hybrid outputs to where the receivers with 26 dB noise figure were connected. You can see here the gain is 0, but this is with an attenuation that I have set here to 50 decibels. So it means the gain from antenna to the receivers is 50 decibels. And as you might recall, the Perseus required daytime an attenuation of was it 15 dB or so, means there is a 35 dB margin for the Perseus, so it is very much better than I need for this antenna. And as you can see here, the worst receiver of them all, the BladeRF at night, directly on the ADC, it required 51 dB of attenuation. So it would saturate directly on the antenna, but very, very little margin, just a little attenuation in front of it, or some selectivity, and it would be perfectly okay on my antenna. The Soft66rtl at night has a margin of 8 dB, and the other ones have a good margin, and certainly, of course, the Perseus. I have changed the frequency scale on the network analyzer and also reduced the attenuation, and this is what the notch filter looks like. And this is not correct at all, because what you see down here is the phase noise. It's not possible to measure these things on a network analyzer like this one. Now I apply just one single signal as the strong signal, and I look in the Perseus. I have set the level when the signal is well away from the notch to show 5 dBm on the S meter, and I step downwards in steps of 1 kilohertz. And you see, not much happens until I come close to the notch here. Oops. And there is a long time constant. And you can see that the depth is about 80 decibels at this point. And the same here. And then on the other side, it is not very wide, it is nearly back at 5 dBm now. I will now step through the notch in steps of 10 Hz, and the level is the same, so outside the noise the meter shows minus 5 dBm. Just like before, I said 5, but I meant minus 5. And the meter is around minus 105. Up to minus 110, and at some point it's only minus 100. And here it is very weak. It's not at minus 112 because that's the noise floor. So go for the worst case, something like this, and the meter shows minus 97. And I set a narrow filter to avoid all the noise, and I still read minus 98. So the worst point in the stop band is at minus 93 dB, and the best point is very much better than that.